All right. So let's talk about this. Questions? Yeah.
So our hope for their grades, what's the weighted total?
That's your current grade in the class.
So like we don't worry about what Canvas says.
Canvas doesn't know how to weight it properly. It assumes that all assignments are worth the same. Whereas homework is much more important than lab and way more important than lecture tutorial. 5 times more important to do the homework than to do lecture tutorial. Right? Because all of that is in the syllabus. That's a more?
Yeah.
Okay. So most of your homework score is your grade. But of course, if you only did homework, if you never put it in a single lecture tutorial and never turned in a single lab, then you would have a 50. And that's not happening. So you're supposed to do all of the different parts of the class, right? Okay. Thank you. And if you have any questions about your grade, or if you feel like, I want more points. I love arguing points. That's my favorite thing to do. Then I get to see if you actually understood what you wrote. Oh, this makes okay. Can we turn the lights on? What's that? What? Asteroid? Well, it's neither of those things. We were seeing galaxies before. That looks galaxy-like, right? But it's not a galaxy. You've seen this picture before today. Nope. Nope. I love all these guesses though. What am I looking at? Something really bright. So we know it's not a galaxy because there's no arms. Do you see an arm here? No, you just did a galaxy. You just did a galaxy classification lab in which you found that you have spiral arms. There's spiral arms here? No. So what is it? Nope. Supernova are circular, right? Is this circular? No, this is a what? Asteroid belt, like a debris disk. Is it the case that this could be a disk, and this could be dust in that disk?
Or is it like forming a solar system?
And is this the formation of a solar system? And these are debris disks or asteroid belts, multiple of them, and the gap in between them is where planets are forming?
Yeah, that was my guess.
That was my guess too. Yeah, I was gonna guess that. That was my good question. Why is big dots? But you know, star too bright, so you put something over it. What? Okay, when you look at the sky, let's say you want to see a plane in the sky, and there's the sun going by. What do?
I look at it directly.
No, you do not. You cover up the sun so you can see things next to it. That's what you've done here, except there's no arm in space. It's an occlusion disk. Does that make sense? All right, here's the picture. This is from JWST. My God, I'm gonna kill this computer. So, you're gonna die.
That's the electric. You throw it out the window.
Okay, no, because it has a lot of research on it. All right.
Probably why.
So this is JWST, and these are the different parts. So there's an inner disk here. There's an inner gap, probably where there is potentially a planet forming. There is an intermediate belt, and then there's this main belt out here. They call it a great dust cloud, and they're looking at like little enhancements in that dust. And they're like, is there like a protoplanet in there? Kind of cool, right? Okay. Let's completely switch gears. Talk about something totally different. I just brought that up because they released it today. Trying to keep you current affairs so you can talk to your parents about it when you get home. I know that's what you also do. Okay, so we have detected leftover radiation from the Big Bang. And interestingly enough, the Big Bang theory, the one that we explode from nothing, it correctly predicts the abundance of helium and the other light elements in the universe, which is kind of strange. You think you start with a bunch of hydrogen, and just knowing a few things, how gravity works, how nuclear reactions occur, and quantum mechanics, you can predict the total amount of helium. And only the Big Bang theory gets it right. Okay, not the show. No discussion of the Big Bang theory in this classroom. Okay. So what is the evidence for it? These two folks, really funny story. Do you want this funny story? Or you just want the facts?
Funny story.
Okay, funny story. Story time, right? Because we're almost done. None of this matters, right? Okay. So no one learned anything in the last week, I'm convinced, and you're gonna see if that's right. Okay, so these two folks, you see this thing here? This is a horn, essentially. You know how like those old-timey cartoons, they have like this thing to hear, help you hear better? That's what they're doing. So this is a big opening, and light goes in here, and it's concentrated down into a detector right there. But the light is not the light that you see with your eyes. In fact, you don't see a single mirror anywhere here, right? This is basically microwaves. Okay? Microwaves, radio waves, it's a radio detector. And this whole thing is on a swiveling platform. It can rotate like this. And so because it can rotate like I'm rotating right now, it can see everything like this, right? In this path. And then all you have to do to see the whole sky is wait for the Earth to rotate. Perfect. So you can see the whole sky through the night, and I can rotate 360 degrees. And I can get radio waves from every direction in the solar system. Okay? And they wanted to do observations with this. And so, did you have a question? So they wanted to get observations, and they wanted to look at like, far away stuff. And they're like, God, there's all this noise, this like excess light that's getting in the way of our observation. And they said there must be a problem. So they go into here, right? And this is like a big thing. They go in and they start scraping off like bird crap, because birds are like roosting in there and pooping. And they're like, this is probably what's happening, is like bouncing around and it's causing this extra light. So they scrape all the bird crap out, doesn't fix it. And they're like, well, okay, so there's this building down here, which is like where they hang out because it's really cold while the observations are running. And there's like a microwave in there. And they're like, wait, let's turn off the microwave. Let's unplug everything electronic. Let's take it all out. It doesn't go away. And they keep trying to find all of these reasons why there's this extra light in every direction. Doesn't matter where they look, right? So they think it's not coming from the sky because it's everywhere that they look. Okay. And they can't figure it out. And eventually they figure out what it is, and I'll show you why. Okay. So that extra radiation is called background radiation, cosmic, because it comes from space, and it's in the microwave. Okay. So I told you that when the universe formed, it was hot and dense, and even light couldn't escape. Would get absorbed by atoms, right? So this is time. If you look on it in that direction, this is hot and dense. This is cold and not as dense. In this part of space, in what's called the era of nuclei, when there is no atoms yet, photons can't get out. They're trapped. And they just become basically energetic protons, and then they become light, and then protons, and then light, and then protons and light, nuclei, like back and forth like this. Okay? Really hot. And then the universe expands enough that light can sneak out. And as it does that, it sneaks out, but it retains how hot the light was at this time. Now you say to yourself, what do you mean how hot the light was? That doesn't make any sense. How hot the light was? That doesn't make a single sense. What? What's the relationship between heat and temperature? Oh, sorry, temperature and light? Is there a relationship?
The color?
Yeah, there's a color relationship, right? So we said something along the lines of, ooh, gross. I need better chalk in this room. Wow, yes. Okay. So we said something along the lines of, you could write something like intensity and wavelength, and it would look like this, right? And where it peaks here is the color, the main color that tells you that something that's less hot would peak more towards the red. Right? So this is red colors, and this is blue colors. Right? And as things cool down, they become dimmer and dimmer. So in fact, there's a relationship between the color of light here and the temperature. Okay. So when this light can finally escape the early universe, it has a very specific color. Okay? Everyone okay with that? Okay. And it's in the visible. It's about 3,000 degrees Kelvin. Visible. Now you think to yourself, whoa, Mateo, you just said that the background radiation was in the microwave, right? What happened? Stretched out. That's exactly right. Okay. Okay. So this is the way to think about this. Imagine it was foggy. Light couldn't get out. It's all trapped by the fog. Okay. And then the fog disappears and you can see far away. Genius, right? Okay. So here is the spectrum that we get. And hey, it looks like the thing I drew, doesn't it? Holy snaps. They might even be related. Okay, so we can grab this temperature and uh-oh, something's wrong. This temperature is only 2.73 degrees Kelvin. What's stretched out? The wavelength stretched out? Why? It traveled. Yeah, it should travel to us, but so does the light to you now. Yeah.
The house be able to move a little bit, so it can't go fully freezing.
Well, so this is, I mean, you can keep waiting and this temperature would go down and down and down. But the reason that it's going down hasn't been addressed yet. Why does it become redder? Why does it become quote unquote colder?
Space is stretching.
Because what?
Space is expanding.
Space is expanding. So these photons that are getting to us have had to travel a much longer distance because the space is literally expanded. So the light started in the visible and now exists in the microwave. Is that crazy? Yes, that's very crazy. Okay. Okay, so this has reduced the thermal energy 1,000 times to microwaves. So you may be asking yourself, well, what does it look like? Okay, this is what it looks like. Like, what the? I'm not looking at anything. That doesn't mean anything to me. Okay, so this, remember this temperature here, 2.73 Kelvin. Okay, this is the average that you're going to see in the next picture. Blue is deviations from it in the negative, and red is deviations from it in the positive. Red, hot, blue, cold. Okay, and keep in mind one thing: the size of the deviation is not here; it's here in the decimal points. Okay, so this is right to like 4 decimal points, and then they're over here. Very, 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 very tiny fluctuations. Okay. Do you see anything? Did it hit a message? Coupon for in and out?
Clumpy.
It's clumpy. Good. Where is it clumpy? Everywhere? Well, it can't be clumpy everywhere.
The right side is more fun.
The right side. So here? So there's a clump, there's a big old clump, but there's also blue clumps and red clumps, right? Okay, there's a clump here, there's some blue clumps here, there's blue clumps here. That's funny. Why would the universe be clumpy?
It's all that where it's like stuff is being like the dust.
What's
Like
that?
where planets are being born and stuff.
Right, so we think about this in the context of planets forming. That's the picture that we saw earlier. Let's scale up a little bit.
Yeah, that's
Galaxy. Right, this is our universe early on
sorry.
collapsing. These places where it's more dense, where it's slightly hotter, there's more material. These are going to be the places that galaxies form, specifically clusters of galaxies. So huge superclusters are going to form in this region. And in fact, when we overlay this, this is what we call an all sky image. So this part here is the same as this part here. And this part here is the same as this part here. It's the whole sky mapped onto this projection. And when we look where the galaxies line up, there are more galaxies in the places that the clumps are, and less in the places where the clumps aren't. That crazy? Okay. Sorry I told you all that. Oops. Okay. So the early episode of rapid inflation solves all of these questions, and this is how it does it. Okay. We want to imagine, either going backwards or going forwards in time, it doesn't matter, that there is some small fluctuations in a surface. As that surface gets bigger, or if you zoom in on that surface, those individual fluctuations will seem larger and larger, right? Okay. So inflation causes those tiny differences to stretch into enormous differences. It's not a very good picture, but this is supposed to be like brighter and that's supposed to be dimmer. And so you'd get more material in the bright spot. Okay. So here's the other question. How can the microwave temperature be nearly identical on all sides of the sky? Well, it's easily explained if we run it back and we imagine that everything was right next to each other, right? Because then the whole temperature is everywhere. Even though I'm looking in that direction, I'm looking in that direction, I get the same temperature. Well, they used to be at the same place, right? So they moved apart like that. We were stuck in the middle. And then the light still came to us afterwards. That make sense? So here's their life cycle. Close friends, super long time, okay? Rapid expansion. We're here in the middle. This is us just doing nothing, okay? And then this is one side of the universe moving away from us. It's the other side of the universe moving away from us. But the light that it emits is heading towards us, okay? And when we get back, it's the same color. Anyone confused, upset about that?
It's three-dimensional.
Yeah, this is one dimensional. This is dimension and time. So three-dimensional picture. Okay. Okay. I want to talk about this. Not really. Okay. So this is the picture that you have in your book. This is the density of galaxies, and kind of looks like that thing we just saw, doesn't it? You overlay them, they work. It's fucking amazing. Okay. All right. So okay. I don't really care about any of these. This is one thing that I like to have people think about. So paradoxes are always fun. When you hear the word paradox on TikTok or on YouTube, it's just it's a way to trick your brain into thinking that physics is broken when really you just don't understand physics yet. Okay, so paradox is always resolvable. Okay, just the people who said it at the time didn't get it. Okay, so this is Olber's paradox, and I'm going to introduce Olber's paradox to you. So if the universe were 1, infinite, 2, unchanging, 3, same rules apply everywhere, right? Then the stars in every direction would cover the night sky, and it would be as bright as day. You say, what? That's the right idea. Well, imagine this picture. Okay, I'm looking into a forest. There are certainly near trees. They cover up the largest part of the field of view, right? But as I go back, there's trees all the way back. So every single like pixel on this image is going to have tree in it. Similarly, if I look at the sky, every single pixel is going to have at least one star in it, if not many, along the line of sight, right? And if the universe is infinite and unchanging, then all of that light is going to shine on us, and it should be as bright as day. If not, way too bright, right? But it's not. What's going on?
Like it's still expanding.
Yeah, it's not changing, right? Or sorry.
It's not a thing.
Good. So it is infinite, but it is changing.
When you say unchanging, you mean like stars can form, but they can't go away, or what does that mean?
Yeah, it just mean that the universe itself can't change. Stars can do whatever they want, but the relative distances between galaxies and whatnot. Okay. Good. Good. All right. So we solved it. That's it. But it's important because it's one thing to think about when you think about at night and you look out in the dark sky and you say, like, this is your first evidence, your first piece of evidence that the universe is both infinite and expanding. You can see with your eye. The reason why it's not as bright at night is because the universe is expanding. And if that doesn't hurt your brain, I mean, like, right? That's the best part. Isn't that cool? Okay, that's the only reason I bring it up. We're only doing cool things in the last week. Actually, that's a very good segue. Okay.
You're
Do I care about this? Do you care about this? No, you don't. Okay. Oh, this one. I don't care about that yet. Okay. Let's ask this question. This is the only one I care about. Over time, the universe has gotten A, smaller, cooler, and more dense. B, bigger, hotter, and more dense. C, bigger, hotter, and less dense. D, bigger, cooler, and more dense. E, bigger, cooler, and less dense. Let me know when you're ready. Let's vote on 3, 2, 1. Okay, a lot of you, but not all of you. Ask your friend, please.
I think you're right.
No, I had one for this one, that's what it-
I think it's spread out.
Yeah, less than-
You ready?
You throw away your straw?
No. Let's revote on 3, 2, 1. There we go. Oh, okay. Yeah. Oh. What's happening? She's changing them. It's ruining me. Okay, so what do we think the answer is here? E. Why E? Expanding means getting bigger. So bigger, so this one's gone. Okay. Anything else?
As it gets bigger, it gets colder.
As it gets bigger, it gets colder. Okay, that's good. So that reduces it to these two. And then?
Less dense.
Why less dense?
It's expanding.
Same material. I didn't add any material, but the volume got bigger. So therefore, the density has to go down. That's what density means. Don't fight about it. It's okay. Okay. Does that make sense? Everyone happy? Okay. So let's do a little quick lecture tutorial. And then I want you to think in your brain hole about what you want to do for the rest of the class. Because I can either teach you the timeline of all life, like that. We can talk about aliens. We can talk about hold on, you can't just be the loud though. Squeakiest wheel doesn't always get the grease, okay? We can talk about radioactivity. We can talk about the rocket age when we went to space. We can talk about special relativity. So I have all these lectures prepared. I'll just pull one up, whatever you want, okay? So think about it first, please. Don't just shout. And please make a new friend. Oh God, I didn't make a new friend.
Yeah.
Yeah, I know. And make a new friend. This one? Who am I missing? Yeah, I want you to make new friends. I gotta get this one goal for you. Yeah. Okay, you guys are new friends? Okay. Who am I friends with? Okay. And if you want to see the timeline, I'll put the timeline slides up so you can just look at them. Okay, let's have a little bit less light. What's that?
Okay.
Rocket. Okay. So what are rockets? Simplified, they are bombs. Okay? But they're bombs that go boom in one direction. Okay? And at the top, we put people. Okay? Or really expensive things. So this here is how you get in. Okay? And you sit in the top here of the big bomb. Okay? What? How spacious, yeah. So this what you're seeing is the Saturn V rocket. If it looks grainy and pixelated, that's because it's from 19 close 67. Correct. Okay. All right. Come on now. Okay, so we'll talk basically. This is a wonderful documentary series from Discovery called When We Left Earth. There are many like these that I can recommend to you if you're interested. You can just put it on while you're studying. It's fucking awesome. You look over and then there's a rocket going off, right? So this whole class or this whole lecture could be a class, and I took one in undergrad that was just When We Left Earth. It was fucking amazing. Okay. So we're gonna do really quick, and we're probably not gonna be able to do any of the physics today. We'll just hit on some of the key points. Okay. So why go to space? Didn't really start with going to space. That wasn't the goal. We just wanted to shoot things better. So in the 13th century, they found out that if you took this like nitrogen powder stuff, you could light it on fire and it would go bang. Okay. And so what they did is they had like, normal fire arrow, but then they said like, okay, we can like take this thing and we can like make fire come out the back. And then it will go faster and hit you harder and owie more. So like you go and then and the guy's dead. Oh, great. I don't like that guy, right? So these are the first rocket designs. They were primarily used as incendiary devices. So let's say, old style, there's no cannons yet. So what you do is you have someone has a castle and you want the things in their castle. And so you say, come out of your castle. And they say, no, we built really big walls. Why would we come out? And we say, well, because we want to kill you. And they say, oh, I don't want to come out. So then you just go around them, right? And that's called the siege. You don't let anyone bring them food. And they get really hungry and then they come out, right? That's a siege. But you can speed it up if you put fire on them. Okay? You put fire on them and they get upset because they don't want to be on fire, right? So then they come out. So this was the first use of rockets as incendiary devices. You would put nitrogen in here or gunpowder in here, launch it over, and then it would explode and catch everything on fire. Cool, right? Okay, guess no one liked that. The first rocket, so you know the national anthem? Everyone knows how to sing it? No, we're not gonna do the whole thing. That's very off key. Scott Key. So there's a line that says, and the rocket's red glare is referring to one of the first types of rockets, the Congreve rocket. So these are actual rockets that were used in war. And they would fly over and they would leave a particle smoke stream as they went over it. Okay? This is the history. I know. It's so many words, Cosmology. I hate you. I thought this was going to be a cool lecture. Okay, so the people you want to know, 1813 is when you first start thinking about what rocket dynamics means. How do we launch rockets? Okay, and in 1861 was the first time people thought, what if we left Earth? And if you think about that for a second, it took less than 106 years from the first idea of leaving Earth in human spaceflight to it being a reality. That's pretty cool. Okay? All right. So, of course, all technological innovation comes from war. So during World War I, they wanted to devastate cities. British and German forces were like, we love killing people, and we want to make sure it happens quickly. So during World War I, they got better and better rockets, and they would bomb each other to Kingdom Come. Robert Goddard of Goddard Space Flight Center is credited with the first liquid propellant in 1926. And this Nazi here is Werner von Braun, begins the production of the V2 rocket, which will be the rocket that we use in perpetuity. So this is the grandfather of all rocketry. He's a Nazi. Keep that in mind. Okay. This is what it looks like. Like I said, it's a bomb. Okay. Here is what makes the bomb go. And here's the bomb. Okay. So what do? So I'm in Berlin. Okay. And I want to shoot London. So it's really just a ballistic trajectory. Okay. It goes up and it comes back down. So all I have to do is kind of gently aim it, right? So I shoot it straight up, and then I have to use some control attitude adjusters. Shoot, shoot, comes down, right? Because like a cannon, you just point and shoot, and it goes, right? This one, it has to go up first, and then it can go. But that's the idea, okay? Okay. So after its development, 3,172 were used against Allied targets. There is no means of stopping these bombs. Okay? And unlike a plane, you don't really hear them coming. Just bomb, dead. Okay? And this is the first human object to cross the Kármán line. So you may have heard about billionaires going into space, right? You saw a picture of Jeff Bezos going into space. He did not go into space. He crossed the Kármán line. The Kármán line is essentially when you go to the beach, and you know, you put your toes in the water and you like let the water go up to your feet. You're like, whoa, but you don't like in the waves. Right? Anyone do that? Or is it just me? Okay. So when I put my toes in the water, that's the Kármán line of space. When I'm like in the waves, right? That is out into space. There's a big difference here. The first human object to cross the Kármán line is the V2. Okay?
That man that jumped off from.
I don't think he crossed the Kármán line. No, balloons can't cross the Kármán line.
No, it was the guy that jumped like from like the furthest part of our.
From a balloon.
Balloon.
Yeah. he can't jump out of a rocket.
It wasn't a rocket, but like.
Okay, so this is important. If you like conspiracies, here's one you do get to believe in because this one's real. Okay, most conspiracies that you believe in are rooted in anti-Semitism. However, this one is rooted in actual anti-Semitism. So what happened was we really like killing people. And so when Germany was getting divided up by the two people who conquered it, here's the Axis, here's the Russians and ourselves, the Allies. We said, hey, you got a bunch of good rocket scientists. Let's have some. And so what they did is they initiated Operation Paperclip, which is where they took 1,600 Nazi scientists and they gave them all US passports and they said, It's okay. Just do war crimes for us now. So let's remember, the basis of NASA is Nazis. Does that mean that Nazis now inhabit NASA? No. Jesus. No.
I don't know.
Just important to recognize, right, that people with very questionable morals used to run some of the best institutions, right? And we have to hold ourselves accountable. So when the reason that we say J.W. Steed and not James Webb is because James Webb was a homophobic bigot. So we don't like him. So he doesn't get to be named the name of our telescope, in our opinion. You maybe that's your ideology. Maybe you like a Nazi. Okay, I'm not gonna blame you, but okay, we're gonna move on. Okay, so this is the first picture from space ever. So they realized, okay, let's put some stuff on the top of the rocket instead of just bomb. Let's put camera. So they put a camera, and they shot it up in a place called White Sands, Arizona, New Mexico, White Sands, New Mexico. And actually, if you go to a graduate program in CU Boulder, you can design your own rockets, and you can go to the same White Sands in New Mexico, and you can shoot rockets off there yourself as a grad student. I have many friends who've done this. And you can put a little camera on the top, and so when it falls back down, a little parachute opens, and you go pick up the camera. It's got a GPS tracker. Great, you take the pictures. At that time, they had to find it. Had to drive around looking for it to come down. Okay. Okay. So that's the first picture of space ever. And you can see beautiful things here, right? Here's clouds, and here's the shadow of the clouds. I mean, you got to squint, okay? It's not high def. Sorry. Okay. So this is the beginning of what's White Sands to what's called Mercury. So Mercury is the first American program to put human beings into space. And the reason that we're doing this, of course, is because we have to demonstrate that capitalism is the best economic value for your buck, right? We are fighting the Russians, and the Russians believe that you should share goods, and that is evil, right? So let's remember that. So we are doing this thing called the space race. Very important. We all believe in capitalism, right?
Of course.
No red scares in here? No communists? Okay. That's fine. Both of them are fake. Neither of them are good for people. So in this particular circumstance, the USSR wins. They're the first people to put something into space. You may have heard the word Sputnik. Have you ever heard Sputnik?
Yes.
What does Sputnik sound like? Yeah, just beats them. Let's see if I have it here. That is Sputnik. Yeah, so they put it into space. It's called Fellow Traveler in 1957. NASA is founded shortly thereafter, and we look really embarrassing for not having our own national space program. Okay, if you go to CU Boulder, LASP, the Laboratory for Atmospheric and Space Physics, the place that I did my graduate degree, is older than NASA. Pretty cool. They're shooting off rockets in the middle of Colorado, just like. Okay, so one month after Sputnik, the USSR launched Laika into space. Okay, this is the saddest part of the story because Laika is a dog. This dog, such a good girl. Okay, so they have a lot of questions, and they're really, really important questions because they, like, for example, we live here on Earth, right? Most people. Okay, so currently we think about the fact that there's blood inside of us.
God has blood too.
Hold on. So when we go into space, will our blood still pump properly? Or does it require us to be dragged down, right? The blood to be dragged down in order to get circulate? Question we don't know. How long can you survive in no gravity? Is it possible to survive in no gravity? They don't know these things. Will you lose consciousness in your brain? They can't just send a human up right away. You've got to test it. So first they send Laika, and they have monitors on her. And she is the first being to ever go into space from Earth. You have the Project Mercury, then born from this, and you see there's a 7 in here. So this is the symbol for Mercury, and the 7 is for the 7 Mercury astronauts, American astronauts, who will go into space. Okay. You don't want to. Okay, I'm not going to answer that. So I said it's said. So what else don't we know about this? Anything else?
Oh, you're right.
At this time, not what we don't know now, but what didn't we know then? Canceled. What's that? Yeah, you need to breathe. You probably need to breathe, right? Like, how do you pressurize a capsule, maybe? Right? How does blood flow? Can you survive multiple G's of acceleration getting off of the Earth? Will micrometeors kill everyone? What are the effects of radiation? Will I die just from the sun being super sunny out there? And can you get them back to Earth safely? So I have to answer all of these questions. So Project Mercury is actually not about rocketry, but about biology. And they were studying human beings. They did very interesting things. They had heart monitors, they had a blood pressure cuff, and they had thermometers in their butt the whole flight. It's crazy. That's a commitment to the bit. Okay? They're literally being launched multiple G's with a butt plug. Okay? That's crazy. So there's no computers, by the way. There's no computers. There's no digitization. You are running on feel. And when I say you're running on feel, I literally mean this. So they'll have in the cockpit when they try to land, okay, they're going to have something that shows them the horizon. They're going to have something that shows them their elevation and their velocity relative to the ground. And that's it. And they will land this without a computer. These guys, the most fucking badass, okay? Because if you fuck up, guess what happens? You die, okay? And you don't just die, you explode and burn up like a meteor.
But it's like that.
Yeah, you check it afterwards, okay?
Oh my God.
So this leads us to Ham. The first US orbital flight was crewed by Ham, a chimpanzee trained to press a button mid-flight, because we didn't actually know whether Leica could do anything. So we needed Ham to do tasks, and Ham did. Good job, Ham. Yuri Gagarin beat us. He was the first human being to ever be in space, the first cosmonaut. Okay. The first woman, interestingly enough, also beat the first American. You don't hear about her very often, but that's Valentina Tereshkov, and that was in '63, very shortly thereafter. Okay. And Alan Shepard, so close behind May 5th. That was the first American. So you hear like Shepard or Alan Shepard. First name. Okay. This is an amazing speech if you've never heard it before. This is from John F. Kennedy. This, you should listen to it. If you like space, this is amazing, right? Because he says, we choose to go to the moon. We choose to go to the moon in this decade and to do the other things, not because they are easy, but because they are hard, right? The idea being that they will create a better world by trying to do something that is difficult for all, right? And along the way, do you get anything from rocketry and NASA? Oh yeah, you get computers, you get the internet, you get everything that we like today comes from the space program. Unfortunately. Okay, so Project Gemini was next. It's the follow-up to Mercury. Gemini is a constellation that has twins, right? So now we're going to send 2 people up at a time. So Project Gemini was chosen, and we're going to do some fun things because the Soviets are doing EVAs. EVAs are extravehicular activities. So we got to do that too because that seems fun. So what does that mean? That means while you're in space, you're going to get out and you're going to get back in. Okay. So Project Gemini did that. First 2-person program being able to make it to the moon. All right, now the Apollo order. So Apollo 1, very first one out the gate, horrible tragedy. 3 astronauts lost their life on the pad, really bad. But, people persevered. Set us back a little bit as far as timing went, but the goal is still to get to the moon before the end of the decade. And Apollo 8 is the first one that we send out to the distance of the moon. And this one's really funny. This is my favorite story about Apollo 8. So they tell the operator of Apollo 8, we only gave you enough fuel to get to the moon and get back. If you try to land, you will not have enough fuel to get back. Because they knew that if they sent them with extra fuel, they would just land without NASA's approval. Because they're test pilots, they don't give a fuck. They're the badass, huge badasses, right? I mean, if you're out there, you're looking down at the moon. So the Apollo 8 astronauts, this is the first picture, right? Where every single human being that has ever lived and ever will have lived is right here, except for these 3 dudes in Apollo. Pretty cool, right?
But they didn't.
So they didn't land. I know. And so the stage for Apollo 11. And Apollo 11 is the one that you know. So this is Apollo 11. The journey to the moon just took over 3 days to get there on the Saturn V rocket, one that I showed you previously. Commander Neil Armstrong took manual flight about 180 meters above the moon. So keep in mind, landing with like control sticks. Okay? On a different planet. Fucking crazy. Okay. And then on July 20th, 1969, at about 7 p.m. Pacific, or sorry, 8 p.m. Pacific, Armstrong became the first human ever to set foot on the moon. Keep in mind, this is broadcast to the whole world. It's coming in real time. My mom was alive, she remembers this. Probably some of your parents or grandparents will remember this exactly. You're like huddled around either a TV screen where they're getting these grainy images in, or the radio where you're hearing his voice from the moon, right? It's pretty wild. It's watched by about 1 out of every 5 people in the whole world. That's pretty wild. Okay. I know, right? So this timing here, so crisp, right? They're like, okay, we're gonna land at 8 to like 11 on the East Coast. That'll still work for most people, right? Okay, no stay up.
Imagine now, like, just having your phone.
Well, like,
Yep.
what's it though? Was it like a weekday?
Oh, I don't know. You can look that up.
Yeah.
I mean, I don't know how you'd be able to sleep.
Very considerate.
I can't. If you were sitting there, there's no way that I can imagine that you went to sleep that night. What a fucking weird feeling. Someone just stepped foot on another planet, That's wild. and you're just like, okay, man.
It was a Sunday evening.
There you go. Perfect. That's it.
I don't know about birthday. That works.
Yeah, it moved on.
Well, I mean.
Oh, from Earth. Yeah. Oh, good question. Let's move back 1 question. What phase is the moon?
We can't see the sun, right?
You don't have to see the sun.
Yeah.
That means it's about to be new, because the sun's like behind the picture.
It's half. Yeah.
What?
Well, it's not the one that's on Earth here.
It's waning.
So if I'm on the moon and this is the Earth,
Sun's over there.
the sun's over there.
It's waning.
So we have the same phase, don't we? Yeah, relative to one each other, we have the same phase. It'll just be opposite in its direction. So this is what the moon would look like, but moonly. Okay. All right. Good. Okay, let's move on. Okay, so how do rockets work? So this is the Saturn V. For scale here, how big is that?
5 stories.
5 stories? Bigger or smaller? Bigger? 50 stories? You know how big a 50, you think a 50-story building left the earth? You know how big 50 stories is? You're gonna make this feel small now. 15, okay, 15, okay, there, that's better. All right, bigger or smaller than 15? Smaller than 15? 20. Bigger or smaller than 20?
You did like what?
Smaller?
18.
18? Bigger or smaller than 18? Okay, it's 19. Y'all almost got it. So let's imagine that for a moment. Anyone here live in an apartment building? How many stories? 2. That
Well, this is really
not really an apartment building. Okay, what's the tallest building you've been in recently?
This one.
This one. So 3 or 4 stories, right? Okay. Imagine, if you will, this is a 19-story building. The person is sitting there.
That'd be fun.
Okay. The size of the person. Okay. Everything from here down is fuel. Yummy. Okay. No, not pollution. So this is not gas. We do not get to the moon based on dinosaurs. Okay. Sorry. Dinosaurs don't burn good enough. Okay. So the things that we want to think about when we're taking off, basically it's Newton's third law. You saw this ad nauseum from every person who wanted to be a faculty member, right? Where you just spit stuff out one side and then it comes out. Okay. So that's what you're gonna do. Okay. So we're not gonna do this, right? Everyone okay? I don't want to hear about it, right? Gas comes out fast, we go up the other way. Okay. All right, so here's the thing. Modern rockets use multiple liquids to ignite. The Redstone's rockets use ethyl, which is alcohol, and water. And mix them together, and then liquid oxygen. And then you just ignite it. So at the very bottom here, okay,
Liquid oxygen.
O2. So you're gonna see a couple things here. Here, do you see how it's like white stuff coming off? That is condensation, because you have to keep liquid oxygen very cold. Otherwise it becomes gaseous oxygen, breathable oxygen, right? The stuff that we love to breathe. Okay, so you mix it with a different fuel in here, and you can see the 2 things in here. So you have the oxidizer down here, and you have the alcohol up here, and they're separated. And you have a little pipe down here. So the oxidant comes out here, and the alcohol comes in here, and they mix in here, and then they ignite. And all you have to do is when they hit each other, they catch fire, and you just push the fire out the back, and you hope the fire doesn't go in that way. If fire goes in this way, what happens?
Yeah.
Bang! Well, no one's in this one yet. No one's here. This is that's a V2. Okay, so this is our Redstone rocket. So this is the Redstone. Okay, so liquid propulsion is harder to store because it has to stay cold. So this is why you see people, right, like they'll fuel it at the last moment. Have you ever seen that? Has anyone seen a rocket launch on like video or anything? Okay, so if you watch the countdown sequence, and I encourage you all to do this, they have like a T minus, and they won't add the fuel until like 2 hours before you're ready to launch. Got to make sure everything's okay, because it's hard to get that fuel back out again, right? It's not like just siphoning out with your mouth, right? Okay. So let's look at the progression as a function of size. Okay. This here is
That's the best one.
Magic School Bus. Okay, this one takes you on a magic ride. Okay. And this is human. This is probably me size. Look, it's got no hair, so that's probably me size. Okay. This is the black arrow. This is the one that we would shoot at no one. This is 1971. Here's the V2. This is the one that we shot at each other. Lots of people died. Okay, this one here is the Blue Origin. So that's Jeff Bezos' weird looking rocket. Okay. Right?
Yes, we.
Okay, and you're going to the right here. So you're going to see some mixtures. So these are the ones that you've heard before. I just said the Redstone. That's this here. Okay, and here, this is a suborbital rocket. And this is how many were successful and how many failed. So 2 and 2. This is a very high success rate. Still quite a few explosions, almost 10,000 explosions, or almost 1,000 explosions. Okay. The New Shepard has never exploded. That's cool. Redstone is 5 successes and 1 failure. Okay, so they're gonna get bigger. So there's the V2 again. There's me. Okay. And as we go along here, we can talk about all these different ones if you want to. But the ones that we start to use in the modern era are in the Atlas and the Titan series. So if you want to put up a spacecraft that you want to send to a nearby star system, or sorry, a nearby planetary system, this is how much weight it can carry. And you see those weights are going up, right? You want to get bigger and bigger objects that you can carry, usually inside of here. So while these are originally designed to be bombs, right? You put the bomb in here, Now you realize, oh, I just put, it's called a fairing, which is basically like a capsule, and then I can open the capsule and I can take the thing out. You put it up here. So that's the Atlas II. Okay, we're getting even bigger. Here's a human. Okay, this is the Soyuz. This is one that they're still sending up. The Russian version. It's got 4 boosters on the bottom. Little babies. Put the humans up here. Cool. The Titan 4 and over here you have the STS. This is the space shuttle system, and this is beautiful, gorgeous thing. Partially reusable. These white ones here on the sides, they fall off. They provide the fuel at the beginning, and then it flies around like a plane and it lands like a plane. It's fucking sick. Okay. Except for its primary purpose, this bay door opens, and then like it has an arm, and it can put satellites into space. Pretty cool. It runs both classified and unclassified missions. Unclassified, we know about them as a human being.
So classified like aliens, like we're giving the aliens.
I'm gonna get I'm gonna get a what is it, like a, yeah. Okay. I was thinking like a beeper that like anytime he says the word alien, it just beeps instead, bleeps it out. Okay, so when this opens up and you put a satellite out, right? That's pretty cool. But you can reverse that process. So you could potentially, let's say you had a beef with someone else who had a satellite that was staring at you. You could go fly up to it, open up the bay doors, grab the satellite, put it inside of your box, close it up, and take it home with you. Kind of cool. No one else ever got close. Okay? The Russians tried. Look at this thing. Two. Okay? Look at this. Wait. Look at this one. 133, baby. Let's go, USA. USA.
They can carry 80,000 kilograms?
What?
Wait, where's the one that you?
Yeah, but it didn't really work very good.
What?
It didn't really work very good.
That's so cool.
Yeah. Okay, twice. Multiply 2 by that, and multiply 133 by 24,000 kilograms. We got a lot more lift. Okay, and of course there's the 2 disasters that everyone knows about. Okay, and down here, these are the ones that you're familiar with. So my spacecraft Maven launched on this one, on the Atlas V. We watched it down in Florida. It's fucking awesome. And these ones here, the Delta Heavies, this is what sent New Horizons. This is what, well, it's not really clear, the Falcon Heavy or the Delta Heavy, which one will send the next astronauts to the moon. Okay, so I haven't even shown you the best one. That's Saturn 1B, right? Where's the Saturn 5? Oh, fuck, where'd it go? Oh, there it is. Okay, so that's the Saturn 5. You have to tilt it because it literally will not fit on the screen at the same time. So here's a little baby person. Okay. Right there. Okay, this big. Good launch capacity, right? What is that?
127,000.
Is that better than the other one? Okay, now you like America again. All right. And look at how many launches. 13 launches. How many successes? 13. How many failures?
1 million.
0. 0 failures. That is good. That's a good success rate.
Somebody drove that. That's crazy.
Yeah, well, no. Up, there's no driving. Up is only up. It's on the way home.
It's
Okay.
landing.
It's the landing. It's the landing. You land this part here. Sorry, yeah. That's unclear. Going up is only up. No. All of this is unusable. So this is a multi-stage rocket. So first, this piece falls off. This is stage 1. Then this piece falls off. There's boosters underneath here that fire. And then this stage is the 3rd stage. There's boosters under here. And this piece here, and this piece here are 3 different segments when you go to the moon. So this piece here is the command module. This is the connector to the landing module that lands on the moon, which is the Eagle. In order for this to work in space while you're orbiting, this part here, this thing comes off. This piece comes off. flips around, and then attaches. Very cool.
So none of that could be used after.
Yes, all of that's in the water.
That's so expensive.
This piece, and this piece are all in the ocean.
In the ocean?
Indian Ocean, yeah. Okay. No, it's not. The money doesn't leave the earth.
Yeah, because it's going into the ocean.
Exactly. The only thing we left on the moon is like one reflective mirror and a flag.
That's a waste of money too.
Oh my god. You waste just as much money going to the store. Target is probably wasting more money than anything else. Okay. Yeah.
So are the other countries like not interested, or they just don't have the money for
For
the
what?
rockets? To have rockets? What?
That's a very good question. And to answer it, you really have to think about what people want to spend money on. We can go to the moon because we are the richest nation on the world. So if I take a little bit of money from you and a little bit of money from you, and I do that to all of our populace, you can have enough money to go to the moon. However, you have to do it within a certain time frame. People have to not get bored, etc. So right now, China and Japan have both attempted to land on the moon. China did. They drove around a little bit with a rover. Japan just tried, I think, last week, and they crashed. So it sucks. Sometimes that happens, right? And so then the question is after a failure, what is the national mood? Does it feel like a waste of money? Does it feel like like either that's a source of pride or whether that's interesting to people as a whole? One of the worst things about the Apollo program, this one, is that we had built already 3 more. And once we beat the Russians and it was clear that the USSR was just breaking up and going to shit, we were like, I don't even care. And even though we had built the rockets, they were like, no, we're not going to pay you the extra money to go and do them. Yeah, it's fucked up. So those rockets, they sit and you can go visit one. There's one in Houston and there's one in Florida. They're beautiful. You can walk next to them. They're absolutely gorgeous. They're so well built that when we're building the next generation, like they didn't have PDFs, they didn't have like digital files. It's all on paper. So some of the paper got lost, some of the paper got destroyed. So they go and they look at the original building of these rockets, and they're like, wow, this is the best way you could have built it. And they use the fact that they're still on the ground to design the next generation of massive rockets. Okay, all right, I think I'm running out of space. I'm running out of time. Landing on Mars is hard. That's the mission here. You can see this is time, okay? The red ones are Russian. The blue ones are the US. If you get to this level, it's a failure. If you get to here, you flew by. If you got to here, you got to orbit. If you got to here, you landed on the surface. And if you got to here, you drove around on the surface. And so you can see that pretty easily. The Russians had a lot of failure, right? We, second time. Fucking geniuses. Second time, right? Boom, boom, boom. Oh shit, we lost this one. That's success, success, success. And then you start seeing down here, different Russia. Okay, this is USSR, this is Russian Federation. Okay, and then failure. And then this one, fail. Orbiter. Okay, that one's okay. Orbiter. There's supposed to be a failure in between here. Oh, excellent. Failure. Okay, so this isn't super updated. I should update this. This was successful. This one was successful. I don't remember this one.
Didn't we get there with the help of Russian intelligence?
What do you mean Russian intelligence?
Contribution by the Russian people,
To get to Mars?
well, the terms that we got, well, that's my term.
No, this is Mars. No, Russians and Americans don't like being friends because all the technology that we're talking about landing on another planet involves rockets, and rockets can deliver humans or they can deliver nuclear weapons. So in fact, we are really good at landing on different planets, and we won't even share with our allies. So for example, this one here, ExoMars, it's not connected, but it is a failure. And what? I know, but this was in 2016 and it's past that. So they wanted to land on the surface and we couldn't even help them. Like we have really good what are called entry, descent, and landing techniques. You can't even share those because it's a violation of American law. America. All right. So these are all the places we've been as of when I made this. We go to
Pretty.
the slide. No, just collected the slides, folks. I didn't make. You think I could draw one word? I can barely write that. The word "the sun" is hard. So these are all the spacecraft we've sent to the sun, to Mercury, to Venus, many around the Earth, many around objects. These are all small bodies that you can't really see well, but you can see better on the slide. And you can see we've been to every body in the solar system. Pretty cool, right? That's the chart of cosmic explorers. You might see your favorite on there. Let's see. There's Maven. Oh. These are all Mars boys. These are Mars landers. These are all Mars, by the way. Mars rover. And then hard to see. These are the Sun boys and moon babies. There's the one that we landed on the moon with, and that's what we left on the moon surface. Okay. Cool. Venus missions. That's it. I think that's all we can do, right? Here's the horizon. If you're curious, this is where maybe some ideas of propulsion are headed. Solar sails is an idea where you use the momentum of the sun's light to accelerate you. And it's slow, but you get to go really fast.
It's
So-
so fast.
It is a slow process, but it will get you very fast over that really lengthy period of time. So if you can use solar sails, great, you can accelerate towards the nearest star system. If you have to survive long enough. Whereas this one here, this is kind of a funny one. Okay. So you put the lid on, and then you pump out all the air, and you go shoot around in a circle till you get to like really, really fast. Okay. And then you open up the tube and you shoot them out the top. Yeah, exactly like that. And the idea is you wouldn't put humans on here, but this would be like a way to like send up fuel and food to people in space, very cheap and fast. Because it doesn't require propulsion, just requires you spinning them fast, right? So this is like a centrifugal accelerator, and it's basically an arm that spins, right? Really quickly, and then it shoots you out. That's potentially plausible. Yeah. What? Not in there, there's no sound. There's no,
When it like opens up. and-
there it goes bang. Yeah, I mean, as it's going out, right? It's so then this one here, this is pretty cool. So what it does is it breaks apart ions. So let's say you start with a hydrogen, and hydrogen has a proton and an electron. You separate them and you push out the electron in one direction, and you leave the ion where it is. It'll give you that same push like we talked about with the gas coming out of the back. So these, very plausible, and they're great for navigating in space. You can't use them to get off of the Earth, though, because if you shoot a beam of hot electrons out of the back, everything will catch on fire and melt. So you don't want the air to explode. That would damage your spacecraft. Okay. All right. Any questions? This is the space race if you're curious. Not a very good picture, but whatever. Questions, comments, concerns? Okay. So sorry that I went a little long, but you wanted to hear about rockets. I guess, whatever. If you want to, you can take this lab, and we can do this right now. If you don't want to do the lab, that's totally okay. If you're happy with your grade and you don't need another lab to bring your grade up, do not do this. If you think you need some extra points because you looked at your weighted total and you said, that's not really where I want it to be, then consider this. The second option is here on Monday, this Monday, a week from today, everything will be due. There is no final in this class. It will not require you to study for a final, okay? However, if you want, I will release, so obviously I didn't release the homework yet, This last homework I'm gonna give you, that's gonna be due on Monday, is just the stuff that we talked about, dark energy, dark matter, cosmological expansion, right? This one here is a bonus homework. We'll have 10 questions instead of 5. It'll be worth 2 homeworks. And it will include questions from the entire year. So if you're looking at your homework score, and you're like, I'm not really doing that good. This one will help. Because it's questions you already answered, and you should know the answers to. Okay? Questions, comments, concerns? Okay. All right, who wants one of these? All right, let's go. 1, 2, 3. Going? Okay, folks. You will need Sharpies. 1 Sharpie to a group. So find a friend. Go ahead, hit the lights. See them?
So, the book, is that only down, still on the.